to get a fast car. I want a ticket to anywhere. Maybe we make a deal. Maybe together we can get somewhere. Any place is better. Starting from zero, got nothing.
We'll start this lecture by discussing quotients of f bracket x, which is discussed at the beginning of section 9.5 of Dummett and Foote. And the first result is just going to follow from a bunch of things we've proven already. So what do we know about f bracket x? It's a Euclidean domain, so it's a PID. We know that in a PID, irreducible elements are automatically prime. You're irreducible if and only if you're prime. So the ideal generated by an irreducible element is automatically a prime ideal. But also in a PID, prime ideals are automatically maximal ideals. We know that maximal ideals are always prime, but in a PID, prime also implies maximal. So prime and maximal are the same thing. So what does that mean? In f bracket x, this PID, every ideal is generated by a single element as principal. And if that element is irreducible, the corresponding ideal generated by that element is prime and therefore also maximal. If that element is reducible, then the ideal generated by that element is not prime. Okay, so what does this prove? This proves the following, which is proposition 15 in section 9.5. Let's say f is a field. The maximal ideals of f bracket x are the ideals generated by polynomials f bracket x that are irreducible in f bracket x. So the maximal ideals are exactly the ideals generated by irreducible polynomials. Okay, so what does that mean? If we now use this fact that the quotient of a ring by an ideal is a field if and only if that ideal is maximal, we see that f bracket x modulo the ideal generated by f of x is a field if and only if f of x is irreducible. Okay, so this is the proof, is we're just recalling these things we already know. So this brings up a natural question, which is what happens if you take the quotient by an ideal generated by a polynomial that's not irreducible? What happens if f of x is reducible? And this is answered with a nice application of the Chinese remainder theorem. So this is proposition 16, which says, okay, let's take g of x in f bracket x and suppose that it's a non-constant polynomial. So the degree is at least 1. F bracket x is UFD, so we can factor it uniquely into a finite product of irreducible elements up to associates. So I'm going to make a choice for something about these elements. So I'll say that let's suppose that g of x equals some unit times f1 to the n1 times f2 to the n2 times fk to the nk, where this u is a unit. What are the units in f bracket x? They're exactly the units in f, which is every non-zero element of f. And I want these fi to be distinct monic irreducibles. So this is not quite how this is said in Dummett and Foote. It just says let them be distinct irreducibles. But by making sure that they're monic, I really want to emphasize that these different irreducibles are not associate to each other. So yeah, so if f1 and f2 are distinct monic irreducibles, then they're not associate to each other. Okay, and these ni's are just non-negative integers, or positive integers, you can say. All right, so then given a prime factorization for g of x, what does f bracket x modulo the ideal generated by g of x look like? Well, it's isomorphic to a direct product of rings where you have f bracket x modulo the ideal generated by f1 to the n1 times f bracket x modulo the ideal generated by fk to the nk. So you can kind of think of this as being like writing a finite abelian group as a product of its prime power order subgroups, right? So we're taking each one of these pieces, these fi to the ni pieces, that quotient, we have to think about what that is. But we just get a direct product where each one of the pieces is like f bracket x modulo the ideal generated by fi to the ni. Okay, so I said that this is just an application of the Chinese remainder theorem. what do we need to make the Chinese remainder theorem work? Is we have a ring modulo the product of a bunch of ideals that are pairwise co-maximal, meaning that the sum of those ideals is the whole ring. Okay, so let's say fi of x and fj of x are distinct monic irreducibles. They're not associated to each other. They generate different ideals. More than that, we know that the GCD of fi of x and fj of x is 1. So the sum of the ideals fi of x, fj of x, that's the same thing as the ideal generated by fi and fj. That's also a principal ideal because we're in f bracket x. And because the GCD is 1, that GCD is the generator of the ideal generated by both of these, is a generator of it. So in particular, the ideal generated by, the ideal generated by fi and the ideal generated by fj are co-maximal. But if you take powers of these polynomials, then the GCD between them is still 1. So the GCD of fi of x to the ni and fj of x to the nj is still 1. So for the same reason, the ideal generated by fi of x to the ni and fj of x, the ideal generated by fj of x to the nj, these are co-maximal ideals when I is not equal to j. Okay, so now we just need to note, if you have a polynomial that's a product of a bunch of irreducible polynomials, that the ideal generated by g of x, that's everything that is g of x times something in the ring, that's the same thing as the product ideal f1 of x to the n1 times f2 of x to the n2 times fk of x to the nk. So what is this? It's the set of all finite sums of things that are of the form something in this first ideal times something in the second ideal times something in this last ideal times. But that means that your some polynomial times f1 to the n1 times some polynomial times f2 to the n2 times some polynomial times fk to the nk. You take all those fi to the ni's together, and you are some polynomial times g. Okay, so now the Chinese remainder theorem applies directly. And when you apply the Chinese remainder theorem, it's saying that f bracket x modulo the ideal generated by g of x, which is this product ideal, is isomorphic to this direct product of rings.